Welcome to lecture 2, Formulating Learning Problems. Goal of today is that you can name the parts of a machine learning solution. I usually have learning targets on 3 different, let's say, levels. The red stuff is, you should just know it. When somebody asks you, you should remember that. Yellow stuff, you should understand that. You should be able to explain it to your spouse, to your parents, to whoever is not an expert in that. If you can explain to these kind of people, you probably understood it well. And you should be able to do something, and this usually has to do with the lab. So all the stuff we hear today in the lecture, you can practice in the lab that follows. So you should be able to remember the parts of the machine learning solution. You should understand I understand that very simple algorithm, but from scratch, like without using libraries, and you should be able to implement that simple algorithm completely from scratch without any library. Why? Because we want, at the beginning, take our time to really think about what makes up machine learning. And I know that probably most of you have covered that material at some point or the other in their undergrad studies or wherever. You know a little bit about that. Just let it be. Just try to follow these steps, implement it later. I think you can learn 1 or 2 things, even if the basic concepts of how gradient descent works are basically something you already know. Good. We'll do that in 2 steps today. We'll first look into what are the ingredients to a learning solution. What makes up a machine learning solution in the end. And then we will go into that concrete example. Thank you very much for closing the door. Into the concrete example of linear regression with gradient descent from scratch. And why is that called concrete? Good. Ready? Let's do a recap of what we covered last week and what you covered probably in your reading and self-study. This guy, Tom Mitchell, had a very nice definition of machine learning that goes beyond the 1-sentence description of making a computer do things that you haven't programmed explicitly. And he talks about well-posed learning problems. What are the ingredients he sees in such a well-posed learning problem? What do you have to pose well in order for it to be a machine learning solution? Can you remember that? And we can contribute with several. Not one has to have the perfect solution. Yes?
Task, performance measure, and experience.
Exactly. T for task, P for performance measure, and E for experience. Can you remember what he means by these things?
A learning problem can be defined as a problem of improving some measure of performance when executing some tasks through some type of training experience.
That's the definition, exactly. We
took notes.
We work on a task, we want to improve on that task as measured by the performance measure by learning from experience. So the experience is somehow the data we have. The performance measure is whatever counts for us, what makes it better, and the task is what we want to do, basically. We will see a bit more on the next slide. Very well. Thank you very much for reading the stuff. Then, this pertains to the last lecture. What are ways how we can classify, categorize machine learning algorithms? How can we distinguish them? How can we say, oh, these 2 are maybe very close to each other. We only have to try one of these. What are ways to characterize machine learning solutions? What do you remember or come up with besides what we talked about last week? Yes.
Supervised and unsupervised learning.
That's a way we can go in the direction of these maps and say we can do unsupervised learning or supervised learning, providing labels or not. Yes, exactly. What else? Yes?
Classification or regression.
We can do classification or regression. What else? Let's imagine the following thing. Somebody gives you a problem and asks you what algorithm should I use, and you listen to the last lecture and you know there are thousands of algorithms, literally. So you don't want to try thousands in order to be sure you have a a decent solution. So you want to somehow cluster algorithms and say, when I have one from this group, I don't have to try the other from the group. I go to a different group. Of course, if you know my task is classifying into different categories, you go for classification and not for regression, for example. But how can you narrow it down without trying all the 500 classification algorithms that you know? Yes?
By classify your data in form of how much data you have, because some algorithm needs a lot more data to learn from them, other need less.
Very interesting. Yes, exactly. You can look on how much data do you have, because some algorithms are more data hungry than others are. And last week we tried to get a better grip on that. Do you remember how we can categorize how data hungry an algorithm is? We talked about the VC dimension of algorithms, the Wapnick-Chervonenkis dimension, that is somehow capturing how adaptive an algorithm is, how many data points it can differentiate from each other in every possible way. This is somehow the definition of VC dimension. And the higher this number is, the more arbitrary decision surfaces the algorithm can produce. And the more arbitrary things it can learn, the more data you have to feed it in order to find out a good surface. Okay? We talked about another concept. This is why I put two things here. One was a theoretical concept of the VC dimension, and we talked a little bit about a theoretical concept also well introduced in chapter 2 of that book, the inductive bias of an algorithm. Basically, the thing this specific algorithm looks for in data that has been hard-coded into its genes, basically. The inductive algorithm of inductive bias of an algorithm. If we have a somewhat understanding of after what does this machine learning algorithm specifically look, and we have another algorithm that has a similar inductive bias, we don't have to try both in the very beginning. We can look for one that looks for very different patterns in the data. And we also covered last week, it's maybe not too practical to look exactly for the inductive bias, because you rarely find it's in structured form this information somewhere. But after a while you gain some experience on, okay, what does this algorithm look for? A very strong inductive bias would be an algorithm that if you have some data points and you're looking for the relationship in the data point that says, it's a linear relationship. Any algorithm that has such an assumption, a strong assumption on the data, hey, the relationship is linear, will work very well if the pattern in the data is really linear, and it will not work at any rate when it's different. So an algorithm that has a strong inductive bias in a specific direction, if you tried this and it worked or worked not, you don't have to try very similar ones. That were the two lessons learned from the theory from last week. And I think we're ready to jump into today's topic. How can we build a machine learning solution? And of course, I understand you already did that one or other way in your life, so maybe it's more about reflecting what have we done in the past. So how do we design a learning solution? When we follow Tom Mitchell, we basically have these three things, right? As you mentioned, we have the task. Could be, for example, we want to learn playing tic-tac-toe. We want to have a tic-tac-toe playing agent, and we want to do that by machine learning, because the game is so complicated we do not want to hard code it, or we are too lazy, or we just use it as an example. So we have a task. I love a task like learn to play that game. We need a performance measure, like what do we count as success? When are we finished? And it could, for example, be if that thing wins a certain percentage of games against the project team members, that's a success for us. That could be our performance measure. And we need some training experience. We said before, we need data to train. And we could figure, why not let it play against itself and learn from self-play? It will generate data along the way and it can learn from that data. So that would be the characterization according to Tom Mitchell. I would suggest to you that this is a rather high-level view. It's not the viewpoint you like to take if you really implement this stuff. It's probably the viewpoint you like to take if you make a feasibility study. Is it possible at all to do something? Is there data around? What is it really that we want to achieve? This is the view you assume when you're writing a requirements document, when you're writing an abstract for a thesis that somebody can select. It's on an overview, bird's eye angle. When you implement the stuff, you have to take a more detailed view, let's say a practitioner's view. And these things, there are three boxes as well. They somehow correspond, but the correspondence is not direct and a little bit complicated. And I want to raise your awareness of that. Yes, you have to know the task, play tic-tac-toe. But if you implement the stuff, you have to choose a representation, both for the features, say the data. How do you want to represent the features, actually, like in code? And how do you want to represent your learned model, your function? So what is your hypothesis space? For example, the features could be the full board state given in a string of X's, dashes, and O's. But you could also encode it with numbers, and you could also encode it completely differently. And you probably made the experience, if you worked on a task where the features weren't given and you came up with them yourself, that it makes quite a difference if you choose, let's say, a suitable representation for your features, or some representation that is not very suitable to program it, to hand it over to an algorithm, and to learn. So there's a difference between high-level saying, I want to learn to play tic-tac-toe on games of self-play, and knowing in detail what's a representation of the work. Same is true for the evaluation. You have to know by what high-level measure you say it was a success now. But you also need to have it in functional form to be able to numerically evaluate your algorithm. That, for example, pertains to the loss function that you optimize. We talked about the loss function last time, and we'll see more of it today. And this is usually not the one that is the standard loss function in your favorite machine learning library. Usually you have to adapt the loss function specifically to the task. And even if your task is simple like classification, and you just want to do use a cross-entropy loss function, you in practice usually have to cope with imbalanced data, so you have to weigh the different classes, and have all kinds of other peculiarities that lead to you have to adapt the loss function in order to tell the optimizer what you really want from the algorithm. Think about this way. The loss function you provide to your learning algorithm is the only thing you give the algorithm to know what it shall learn. You as a human has a lot of context information on what it means to play tic-tac-toe. You know I cannot win, but in best case I do not lose. All these kind of things you already know. Your algorithm knows nothing about that. It just gets a loss function that optimizes it mathematically. So every task specificity that needs to be known to the algorithm in order to find a solution in a good way, a quick way, and a good solution, you have to tell him the algorithm in the loss function. And of course, evaluation is not just the loss function. This is how you provide a learning signal, so to say, to the learning algorithm. Evaluation is also how you count later your errors and what do you plot in order to see how I am progressing. Of course, you can plot the number of games this thing wins against humans. If you do classification, you might be tempted in the beginning to plot accuracy. How much of the predictions I make are correct? That's a good measure. When your training data and your test data is balanced. If you expect much more decisions on one side than on the other, like for example, you want to classify if somebody running in front of a camera is a terrorist. You expect that 99.9% of all the guys running in front of the camera are not terrorists. So you can get an algorithm with 99.9% accuracy by just saying nobody's a terrorist. You don't want that. And that there you want another performance measure, for example, recall or precision on the terrorist class. Okay, we'll talk more about that next week. Evaluation does not directly, like the technical evaluation, does not directly follow from the high level, oh, when we achieve that, we are good. That is the story here. It's not a direct correspondence. You have to think about it, and that thinking is sometimes hard. Last thing, you have to choose an optimizer. And maybe this is also new to some. If you think about machine learning, not just as somebody having a machine learning task to solve, but as somebody who starts diving into that field of study, you realize a machine learning solution is not all this tied together and a package that cannot be separated. These are different entities, and you can combine them as however you want. You can choose a neural network here to do the mapping between inputs and outputs, and optimize it by the standard thing for neural networks. What is the standard thing for neural networks? Did I hear gradient descent, backpropagation, all these kind of things? Yes. This is what you would usually do, but nobody in the world says that neural networks have to be trained by backprop, meaning gradient descent. You could train it by genetic algorithms. You could train it by a dozen of other different optimizers. Of course, it somehow makes sense to train it by backprop. But this is not a marriage relationship. Some combinations go well together, but it's not that it's predetermined. So you have to choose, what do I use to train this representation? What kind of optimizer do I use? Maybe we see that better on that slide. From the three things you have to choose, the representation of the hypothesis and the features, the evaluation criterion, the loss function, the performance measure you take technically, and the optimizer. Not all combinations in that triple are valid, but much more than you think are valid and are actually worth trying. So it makes really sense, if you think about machine learning, to think about the representation, evaluation, and the optimization separately, and choose what suits your specific case. See it that way. If you have a standard machine learning problem that has been solved 100,000 times already, then it's probably the standard thing. The standard loss function with a standard algorithm that everybody uses for it with a standard optimizer. But then it doesn't need you to solve it. Then this will probably be done by automated machine learning. If it needs you, like an expert, somebody who studied it, then it's probably because it's not the standard thing and you have to think about this combination. This brings up the question, how do you select these components? Like, how do you come up with it? And there are a couple of different twists to the answer. One is, it takes experience. The experience you can gain by doing it yourself. You can also read about it and learn from the experience of others. Next twist on it is we will talk about exactly that question a lot in that course. It will pop up at different points during the course. What I want to give you here as somehow a gut feeling kind of advice is, if there is any prior knowledge you have about the machine learning task, the thing the machine has to learn, that can easily be expressed in features or models, you should do that. It's not like, I'm somehow cheating if I tell the machine learning solution this already, because it should learn it itself, and if I provide all this information, it's not learning anymore. That's a very good thought if you're a PhD student and want to do something really novel and the next breakthrough, but probably for just solving the next problem, and even as a PhD student, who sometimes just solve problems, think about what prior knowledge you can encode in the features and in the models. You know that the relationship is linear, then please use a linear model. It makes sense. It's not that you should use a neural network then and let it figure it out itself. That's where you should use the English word stupid for. Good. What else is such a gut feeling tip? Hint. It's much more important to have good and compact features than to have the perfect learning algorithm, like model plus optimizer. Features are more important than models. The data is more important than models as well. So you can be guided by the following principle. If you see the pattern you want the machine to learn to pick up, if you see that in your features as a human, then probably the machine can learn it as well. If you or the expert that is an expert in the problem doesn't see it in the features, not at all, like I don't mean like with the blink of an eye, we see that for example in images but not in tables. There we have to look specifically. But if we are not able to do the classification task or the learning task for ourselves based on the features, like you don't have to start. It will not work. You have to see it as a human. Yes.
Features.
The axis, the data matrix you feed to the features. What the statisticians call the covariates. If you don't see it in the data that you feed the algorithm, then it will probably not work. The other way around, if you see it in the data you provide, it should be able to learn by machine.
Do we as humans not have a problem with multi-dimensional problems where it's very easy for the machine to learn something, but we can't imagine it because it has 7 or 13 dimensions?
It's a rule of thumb. There are, of course, things where we as a human can see something very easily and it's complicated for the machine. And there are things where we as humans have a very hard time and it's very easy for the machine. But as a rule of thumb, I think this happens. More questions with respect to that? Take-home message here, a machine learning solution is not I take a neural network, or I take a support vector machine, or I do it with a decision tree. A machine learning solution is to think first more of the features, more of the data than of the model. And if you think of the model, you have to think about representation, evaluation, optimization separately. It's not a fixed combination. You have much more options. And sometimes the path to a good solution lies in choosing a good combination. You can read more about that in that paper from Pedro Domingos. I think it's called A Few Useful Things About Machine Learning, something like that. And it's on Moodle in the supplementary material very much at the bottom of the page. Good. Let's try to formulate some machine learning solutions. I borrowed these quizzes to some extent from Andrew Ng, who is doing a great course in machine learning. And I found these rather easy, but they have some twists to it. Maybe it's not so easy, but we will see. Suppose we feed the learning algorithm a lot of historical weather data and have it to learn to predict the weather. In this setting, what is its training experience E? And you have 4 options. Maybe you check them quickly, and then we do it just with hand signs. So maybe we start at the bottom. What is the training experience E, the weather prediction task? Okay. The process of the algorithm examining a large amount of historical weather data. Roughly maybe 10 people, 20% or so. The probability of it correctly predicting the future date's weather. These are another 20% roughly. None of these. That's maybe 10%. Thank you very much. What is the training experience when I'm feeding a learning algorithm a lot of historical weather data? The training experience is a fancy word for the training data. Training data in that example is the historical weather data. Meaning all these things are very elaborate sentences of bullshit. And I successfully tricked you, or Andrew tricked you. It's none of these. Actually, the training experience is historical weather data, and all these other stuff here is whatever, different things, but not the training experience. Good. Let's go to the next one. Suppose we are working on weather prediction again, and use a learning algorithm to predict tomorrow's temperature in degrees Celsius. Would you treat this as a classification or a regression? Let's quickly think about that. You want to ask something or answer? No, why not answer?
I would say regression.
Why?
Because it's a prediction and the classification is more within some folders.
It's a prediction of any scalar values, so it's not just putting it into bins, into folders, so you say it's regression. Does anybody want to challenge this answer and give a different one? It's a safe answer, by the way. Who would actually in practice treat that as a classification problem?
It depends on the data,
Why?
because we can have only classification in the data, meaning that we have only sunny, rainy, or cloudy.
Ah, okay.
And then it's a classification problem, because we classify the data in number.
Okay, but it says here we want to have it in the end in degrees of Celsius, so I suppose the data will somehow warrant that. Yes?
You can have classes from 10 to 15 degrees or from 15 to 20 degrees, and then treat it as classification.
You suggested, I just repeat for the recording, you suggested to somehow bin it and say let's make a class for 10 to 15 degrees and 15 to 20, or maybe a finer grain binning, and then we could treat it as classification. Are there advantages or disadvantages to that? Thank you very
If
much.
I have the data in this form, it's not as representation.
If the data is already in that form, that's very suitable, yes. Are there other advantages or disadvantages?
It could be.
We might have to label the data we used before.
Pardon?
So we have to type in which label or which class it is.
We would have to come up with the binning by ourselves, exactly, yes. That makes create some work for us. We obviously also lose precision, like if we do a numerical prediction, like regression, we can say like, oh, this is 19.786 degrees Celsius today, at this moment. And if we just classify in bins, like from 19 to 20 and 20 to 21 and so on, we lose precision. But one could argue that in order to really predict it up to the third Nachkommastelle, up to the third, thank you very much, up to the third decimal. If we want to predict in that prediction, we need a lot of data to accurately do that. And it could in fact be, if we have not huge amounts of data, it could in fact be more honest to just say, hey, it's 20 degrees, if it's or 21 or 19, but not more precise. And then we could actually do the trick you mentioned, do a binning, treat it as a classification problem, because we know classification, when it's not huge amount of classes, usually gives us more precision. Like, will work better. It will not predict more decimals, not precision in that sense, but the actual prediction will more often be correct. It's easier to do classification than to do regression. So that is actually, there's no true and false here. You can argue in both directions. It's somehow a design choice you have to take. The straightforward thing is to do regression, but there might be good reasons to treat it as a classification problem as well. Probably if I would work on that, I would start with regression, build the best model I can, and then invest a day or two to build a classification model as well, and then compare it. Good. Suppose we are working on stock market prediction, and we would like to predict whether or not a particular stock's price will be higher tomorrow than today. You want to use a learning algorithm for this? Would you treat this as a classification or a regression problem? Who is for classification? 50%, 60% maybe? Maybe even 70. Who's for regression? That's only 5%. Okay. Well, somebody who said classification. Why classification? Yes?
Because you only want to know two classes. If it's higher, then you have a 1, or not, then it's 0.
Exactly. It's a binary classification task. You have two classes. It's higher or not than yesterday. So you can treat that as classification, which is a simpler thing if you can frame it like that. So I would also do that as classification. You actually, of course, you could try to predict the next day's stock market price as a number, as a scalar, and then see the difference, and from that deduce automatically if it's higher or not. But that's a much more difficult task. There's a very nice saying by Vladimir Vapnik, the guy who came up with the Vapnik-Jabolinkis dimension and who invented the SVM, so quite a figure in the field. He said, I think we have the quote next week on the slides, but he basically said you shouldn't try solving a more complicated problem than you have. It usually makes your accuracies go down. So if you can treat that as binary classification, please do it. 4. We have a couple of examples here what you want to do, and we want to know which one you would apply supervised learning to and which one you would apply unsupervised learning to. Let's do it one by one. Supervised or unsupervised is a question. Examine a web page and classify whether the content on the web page should be considered child-friendly, for example, non-pornographic, or adult. Would you do that with classification? With supervised learning or unsupervised learning? Let's see who's for supervised learning. Half of you. Okay, some people, more than half of you. Who is for unsupervised? Very, very few. What would you say why unsupervised?
Because the clustering problems, you have to cluster which content would be like child friendly and which is not.
You would treat it as a clustering problem.
Yeah.
Okay, yeah, then you would use unsupervised learning.
Yeah.
Of course, it's somehow depend on your viewpoint. If you say, okay, you could also say two classes, child-friendly versus adult, and then it's classification. Probably, usually you have a better outcome when you have the chance to do supervised learning. You have a better outcome with supervised learning because I would formulate it that way. You can give a stronger learning signal to the algorithm if you can provide it with correct answers for every possible input. If you do that, you provide a stronger learning signal to the algorithm. So if you can treat it as supervised, I would treat it as supervised in general. There is another point to mention maybe for specifically this example, like child-friendly or not. I once was at a conference on multimedia analysis and was looking at the poster session at the research the other PhD students were doing. I was a PhD student myself then. And one showed visual classification of exactly that stuff, but of the stuff that is not just X-rated or child-friendly, but of the stuff that is actually where the police is interested in or not. And I was asking him, like, okay, how do you do that? And he said, yeah, the last 3 months I sat in the lab and classified images as child pornography or not. I said, gosh, you actually don't want to do that, and you actually don't want to force other people to have to do it. It's like, there's another problem here. This is not a machine learning problem, this is an ethical question. Like, should we pay people for looking at such content for extended periods of time, and what are we doing? Maybe there are people that think it's a great job to look at pornography for 10 hours a day and get paid for it, but I'm not sure if that actually is very helpful. Okay, let's go for the next thing. You want, again the question is supervised, unsupervised? Examine a large collection of emails that are known to be spam email to discover if there are subtypes of spam.
Unsupervised.
You would say unsupervised
Find,
because?
New patterns.
You want to find new patterns, exactly, and you are not sure yet what these patterns are. This exact formulation cries out for an unsupervised clustering method. Like, you want to detect subtypes, but you don't know yet if there are any and how do they look. That's clustering. Yes, unsupervised. In farming, given data on crop yields over the last 50 years, learn to predict next year's crop yields. Supervised or unsupervised? Supervised. We have the past data, we know input and output relations, we can learn from that. Yes, exactly. Last one. Take a collection of 1,000 essays written on the Swiss economy, find a way to automatically group these essays into a small number of groups that are somehow related or similar. Who's for unsupervised? You are right. This is the same as this one. It's about finding groups, finding patterns you don't know about yet. That's a typical clustering use case. Remember, unsupervised learning is not just clustering, but it includes clustering. Yes?
In the first question, I have just a short one.
Yeah.
Child-friendly and adult, would you provide data for both categories or just say, oh, just one interested in adult, so I just feed in adult and everything else is child-friendly?
The question is basically, would you feed in label data for both classes, do binary classification, or just give data and labels for one class and then basically do something that we call anomaly detection. Usually you have better results if you have these data and the classes are balanced, if you have labels for both, because you can better learn the line of demarcation between two classes. If you just have data for one class, you have to accurately model this class in all its aspects without knowing against what you're modeling. So this is a more difficult problem. But sometimes it's more easy to frame it like that because you only have data over one class. Think, for example, in predictive maintenance, you have data about some engine or some other mechanical device and you want to know when does it break. Usually you have loads of data when it runs well, and you have very, very few occasions when it actually broke, because usually the operators don't let it break. So you just have data of one class, and then you go this way. And there are good methods for it, but the easier problem is if you have both and just learn the line of demarcation. Okay, last one, and this will launch us into the second part of the lecture. This is about burning stuff and making fire, so this is cool. There are many substances that can burn, such as gasoline or alcohol, and they have a chemical structure based on carbon atoms. For this reason, they are called hydrocarbons. A chemist wants to understand how the number of carbon atoms in a molecule affects how much energy is released when you burn them. So he obtained the data set. You have a number of molecules here. You see the number of carbon atoms in it, and you see how much heat is released. And somehow ignore the negative sign if you don't want to understand the chemical context. The larger negative this number is, the more energy is released. So, is that classification or regression? That's somehow regression. Yeah, I would also say so. And what is the training data here and what are the labels? Which of the columns? I think we start with the labels. What is the label here? If that would be framed as a regression machine learning problem. What is our target? Yes?
The heat released?
The heat release, the last column. Yes, exactly. This is what we want to know. We want to give in something else and want to know how much heat is released when I burn that up. What is the data we give in? What is the training data? Yes?
Number of carbon atoms.
Number of carbon atoms, yes. What's about the name of the molecule?
We don't care.
We don't care. Exactly, this is garbage for us. We ignore it. Right. You could come to the conclusion that you want to feed the algorithm also the text, but that makes the problem a whole different kind of thing. Then you train it actually to, I don't know, you should not care about that. Good. Now, if you just look at the table, what would you say, what is the relationship between the input and the output, the X and Y, the training data and the labels? Yes?
Close to linear.
How do you see that?
They're like parallelly increasing. Oh, sorry, decreasing. Yeah.
So this is increasing, this is decreasing, yeah, but it's somehow, it's a proportional thing. This always gets bigger, this always gets, let's say, also bigger when we ignore the minus. Could be linear. How could we be more sure? What could we do? You could plot the data. Yes. For those of you who never had the chance to sit in a data mining class or some other data analysis class, not specifically related to machine learning, exploratory data analysis, like looking at the stuff you want to work with, is actually vital. It's super important. So the first thing you should do that is somehow possible is to get a feeling for your data, for example, by plotting it. And this data is made for plotting. Like two scalars that you could plot in 2D, we would come up with such a plot. And here we already see, yeah, could be linear. Not too bad. Actually, plotting such stuff, even if you don't use any tool, but just write Python code, is rather easy. So this code is completely runnable, opens an Excel file, loads in the data, produces a plot, Python 3 code, executable as it is. So this kind of stuff, exploratory data analysis, and then trying something simple first before you shoot with cannons on whatever is there, are the really low-hanging fruits you should exploit. Even in research, if you want to come up with new machine learning models, you should start with the simple stuff and see if it already works, because in the end you don't want to solve a problem that wasn't even a problem with some complicated method. You go for as simple as possible. And only if you encounter a problem that cannot be solved with anything you know, there's a research question down there. I can approach it with something new. But until then, do the simple stuff.
One small question. We have the situation at 8 molecules.
Yeah?
We have kind of a settle point, because after that the value increases again, or decreases negative side. When should we take respect to that, and when we can ignore it?
You mean outliers and stuff like that?
I mean, if we took a parabolic approximation here, maybe we would be more accurate with 12 and 14 and 16. Or are there just no data? And if no data are available, I cut off the 10, or I take the linear regression.
So the question is, when should we take respect that it looks to be linear up to here and then it goes up again?
Yes.
And shouldn't it be a polynomial instead of a straight line? These are all questions that come up in modeling. Maybe you, in the end, just try. This is something we do very often. We're in an empirical science here to a large degree. We have to try things, so we have to do valid and very structured experiments. But I would interpret it like that. It's basically a straight line, but the more molecules we have, it somehow the spread becomes larger. This is basically just a spread right here. So even with a simple thing, there are obviously two valid explanations what could happen, and it would be up to making experiments to see what gives us a good prediction. Okay. So I quickly, before we go into how to implement that stuff from scratch, because that's the goal of today, I want to go over the machine learning process for all of you who haven't thought about that yet. Maybe this is especially important for computer scientists. Who, by the way, were the computer scientists here? Okay, so you probably have been well trained in software engineering, right? You learned how to develop good programs, write clean code, right? And you learned about database design and how to arrive at a valid database model. The important point is that modeling data is a distinct thing to do. It's not something that you can approach with your software engineering mindset if you have it. You can switch it on. You don't need it in modeling data. You also cannot do it with the same mindset you try to model business processes. It's a different thing. You cannot do it with the approach you use for database design or for statistical analysis. Doing machine learning is somehow a little bit different. Of course, still it has lots of overlap with all of them, but it's something different. If you build a machine learning model, you start with exploratory data analysis, meaning you look at the stuff, you make your hands dirty, you start with code, but you don't want to write nice code that is reusable and that is version controlled and everything. You just hack a few lines of Python code to see the thing or load it into a tool. It's not about the code. That's important for the computer scientist. And then you focus on systematic experimentation and rigorous evaluation. Systematic means you not just try something and then you think, oh, okay, try something else, you do something different. You do it systematically. You think about what do I want, what do I think might be a valid model, and you try the different options. You sample from the different values of your hyperparameters in a systematic way, and you do rigorous evaluation. That does not mean you sometimes look at the plots and you, it's not good, I try again. But you measure all the figures of performance you should measure, and you record them, and you draw valid conclusions from them. You really analyze that stuff, but you are driven by experimentation. Coding is important. You cannot do that without writing code. The things we look into when we are in a machine learning class and later an application cannot be done with some click tool. You have to code, but it's not about the code, and it's usually not so much about the reusability of the code. So writing clean code here is not the main focus. If you are able to do that, all the better, but you shouldn't invest too much time into that. The focus is on experimentation. I usually have to make that clear to my fellow computer scientists, because I myself am one and had to learn that the hard way. Okay, how do you do that? The best thing is not to have a monolithic solution that can do everything, but to have a pipeline of small scripts, a pipeline for visualizing stuff, a pipeline for removing outliers, another script for training a model, another script for analyzing the results and producing the figures of merit, and so on. That reminds me very much of the way you work on the Linux shell, or Unix shell. Small, dedicated programs that exchange data over files or over the standard in and out, and you pipe them together. Why? Because then you can quickly exchange something. If you write a huge monolithic software solution, it's very hard to maintain, and you will focus in the end on software development instead of experimentation. So I would advise you to use something like that. Doesn't mean you have to use Linux. You just have to adopt this approach of writing small, dedicated scripts that do a specific thing, save a file, and write the next thing that opens the file and does something with it. Because then you can also work with the tools that are best suited. You can write the one thing in C# because you just found code that does the trick to 90% already, and do the next thing in Python because the library is only in Python available, and do the next thing with some graphical tool because you can just click there, even if it's proprietary software and you have to pay for it. But that will make the best out of your time as a developer. So that would be my advice. And for the data exploration stuff, please use rapid prototyping. Don't spend weeks on writing a software and then maybe you don't need it. Do rapid prototyping, and what I really like to do there, if it includes plotting data and playing around with it, use IPython or Jupyter notebooks. They are really nice for interactively acting with data. You could also do that with the R stuff, but as a computer scientist, you cannot advertise R. So I advertise IPython. Fine. Questions up to here? That's all basic stuff. You probably know most of it. It's just important to have the foundation. Again. Let's do the following. 5-minute break, and then we go into the second part, machine learning from scratch.